This lecture introduces definitions of a matrix, and we talk about the coefficient matrix of a system of linear equations, and also about the augmented matrix of a system of linear equation. So first, what is a matrix? In mathematics, matrix is an array, right? A rectangular array of number symbols or expressions arranged in rows and columns. So a matrix with m rows and n columns are denoted by m by n matrix. For example, you can say a matrix A. A matrix A is 2 by 3. That means matrix A has 2 rows and 3 columns. And we call a matrix is a square matrix if the number of rows is the same as the number of columns. So in translating a linear system to matrices, there are 2 different matrices that are associated with a linear system of equations. The first matrix is the coefficient matrix. So the coefficient matrix is a coefficients matrix of a linear system. The linear system of equations is a matrix that contains only coefficients of all the variables of the linear system of the equations. For example, if you look at this linear system of equations, it's the 3 equation with 3 variable x1, x2, x3. And 3 here is the coefficients of the first variable x1 on the first equations, right? And x2 here is the coefficients of the second variable x2 of the first equation, and so on and so forth. So from this equations, from this system, we can translate this system into a coefficient matrix of a coefficient matrix of this linear system. And this is the coefficient matrix of the system here. As you can see, that 3 represents for the coefficients of the first variable. And 3 is on the first row. That means is the coefficient of the first variable of the first equations, right? And then negative 2 here is on the first column and the second row. That means negative 2 is the coefficient of the first variable of the second equations, and so on and so forth. So this equation here is this matrix here is a matrix. It's 3 rows and 3 columns, so it's 3 by 3 matrix. Okay, you have 3 rows and 3 columns in this matrix. And each of the entry of this coefficient matrix is the coefficients that corresponds to the variables and to the equation that coefficients is on. All right, so from one linear system of equations, you have a coefficient matrix, and you also have a augmented matrix. So an augmented matrix of a linear systems is a matrix that contains first coefficient matrix, right? All the coefficients of all the variables. And you have a vertical bar separating the coefficient matrix, and this is called the constant matrix. So you can say it's this constant column or a constant matrix. Okay, so where do you get this constant matrix? So these constants are coming from the constants on the other side of the equations. So you have 3 equations in this system, and on one side you have variables, on the other side you have constants. And this is And the constant column or the constant matrix here is formed using this constant on the other side. So if you can see that this is the augmented matrix. Augmented matrix contain first the coefficient matrix, right? And then with a vertical line separating coefficient matrix and the constant matrix. So now instead of writing this system of linear equations with variable x1, x2, x3, you can use its augmented matrix to represent the same system. And then when people look at this augmented matrix, they know that this is a system of 3 equations, 3 variables, and this is the augmented matrix that representing for the system of 3 equations with 3 variables. But then if you look at this, if you use this augmented matrix, then the size, right, of this matrix should be 3 by 4, because you have 3 rows and you have 1, 2, 3, 4 columns. All right. So again, these two matrices here are associated with the same system. But if you use just the coefficient matrix, that means you have no idea about the constants on the other side, right? But if you use the augmented matrix, then you know all the information of the system. All right. So in matrices, there are elementary row operation that you can apply to matrices in order to achieve equivalent matrices. Okay. And then the two equivalents, I mean, you can say that the two matrices are row equivalent if there's a sequence of elementary row operation that transforms one matrix to another. Okay. And then these here are the row operations that you can apply to a matrix so that the new matrix, the result matrix, will be row equivalent to the previous matrix. All right. So as you can see that we know there's 3 operations on a linear system of equations to obtain the two equivalent system, right? And those operations are corresponding to this row, elementary row operations when you use matrices. So the first row elementary row operation is interchange 2 rows. So if you have a matrix and you interchange the order of the 2 rows of the matrix, you can do that, right? You're obtaining a new matrix that is equivalent to the previous matrix. The second elementary row operations is multiply a row by a non-zero number, non-zero real number. Okay. To obtain an equivalent row matrix, you can pick one row and you multiply that row to a non-zero real number. Sometimes people call it as a row scaling operation. All right. And then the third row operations, elementary row operation, is you can replace a row by its sum with a multiple of another row. Sums or a difference, right? With a multiple of another row. That means you can pick one row, that means you can pick one row, right? And then you add or subtract that row with the multiple of another row and replace that result. Replace that row by the result. Okay, well, let's try an example here. Okay, so this interchange 2 rows, let's say row 1, you interchange to row 2, right? You multiply a row, let's say row 2, and then you take 3 times row 2, right? Or you can replace row 3 by row 3 minus 3 to row 1, for example. So these are the elementary row operations that you can use on a matrix to obtain a row equivalent matrix. All right. Now let's look at an example. Use elementary row operations to reduce the augmented matrix, right, to a strict triangular form if possible. So if you look at this augmented matrix of a system of 3 equations and 3 variables, so you have 3 equations, 3 rows, and then 3 variables here, and then this is the constant matrix. So how can you, and remember that the strict triangular form is a form when you have something like this, right? So you have R0 here, R0 here, and then non-zero here, right? And then then you have this, and then you have a constant. Okay, this is non-zero value right here. And again, the strict triangular form, you only need to obtain the strict triangular form for this coefficient matrix. You can ignore. You don't have to make a strict triangular form for the constant. So just look at the coefficient matrix and try to transform it to a strict triangular form if possible. All right, now we can, so the first coefficients of the first variable on the first equation is non-zero, so which is good. So we just keep it. We don't have to move it, right? But we need to make this coefficients and this coefficients equals to 0. We need to zero these out. Okay, so then we can achieve the strict triangular form. How can you zero this out? First, I want to look at the second one. So it's -2, and I want to replace the second row. I take the first row, replace the second row by its sum with a multiple of another row. So my point is I want to use R2. And I see, and you can see that -2 and 2 here, right, is tempting that I can just add this 2 row. So I take row 2 and add to row 3. See what happened. Well, if row 2 add to row 3 and I replace this operations, I replace row 2 by row 2 or row 3, I will get this. So row 2 will be -2 plus 2 is 0. 1 plus -1 is also 0. -1 plus 2 is 1. Don't forget the constant matrix. 2 plus -1 is 1, right? So this is my new row 2. And I didn't do anything with the first row, so I should keep it as it is. And I didn't do anything with the third row, so I should keep it as it is. All right, now, well, my goal is I have 2 0 up here, right? But I need 2 0 on the last row. So I think I would try to switch the order of row 2 and row 3 because I want the last row to have 2 zeros. So I do that. I keep the first row. I move the second row, the third row up to the second row, and I move the second row to the last row. Okay. Now, if I need to, the next step is I need to zero this out. If I zero this coefficient out, I can be done. Okay. So how can I zero this out? So at this point, I know that I need to use the first row to zero out the second row. So I will replace row 2 by row 2 minus 3 over 2, row 1. Okay. I'm using 3 and 2 to zero the 2 out. So why do I know? How do I know that I use R2 minus 3 over 2 R1? I do it in my scratch paper. So 2, right? 2, if I minus 3 over 2 times 3, then, so it should be 2 over 3. No, 2 over 3, yeah. See, so I need to have 2 over 3. 2 over 3. So I have, hold on, I have 3 here, right? 3 is the coefficients of row 1. 2 is the coefficients of row 2. I want to zero out row 2. The coefficient of row 2, I need to take 2. And because it's the same sign, I have to use the minus sign. So 3, how can I have it 2? So you have 2 here and then 3 here. So 2 over 3 should be the coefficients of my row operations. So that means this is row 2 minus 2 over 3, row 3, right? Okay, now I have to go here and I can change this. Should be 2 over 3, row 1. Okay. So this is the operation that I'm going to do, and I replace this operations. I will replace row 2 by this operation to achieve my goal. So I keep the first row as it is. The second row will be 2 minus 2 over 3 times 3 should be 2 minus 2 is 0. The negative 1 should be negative 1 minus 2 over 3 times 2, right? Here, and then 2 minus 2 over 3 times 1. So I kind of do it on the scratch paper on the size to then, so then I can calculate this coefficient, the new coefficient, accurately. So negative 1 minus 4 over 3 is negative 7 over 3. 2 minus 2 over 3 should be 6 minus 2, it should be 4 over 3. And then the last one is 1. Negative 1 minus 2 over 3 times 0 is just negative 1. Okay, and then the last row, I keep it the same. Now I look at my new matrix, like arithmetic matrix. It's still arithmetic. Is it in strict triangular form? I ask myself that questions. It is, because I can kind of form a triangle here using the non-zero coefficients, right? I have the upper triangles are non-zero coefficients, and then the lower triangle are all 0 coefficients. All right, so I just use some elementary row operations in order to reduce an arithmetic matrix to its strict triangular form. And as you know, that we wanted to reduce this to its strict triangular form because we want to solve it in an easier way. And again, the definition of row equivalent is if the two matrices are row equivalent, if there's a sequence of matrix elementary row operation that transforms one matrix to another matrix. So if you look at the original matrix, so the original matrix that we worked with is this matrix. And then I use a bunch of row operations in order to get to this strict triangular form matrix. Okay, those operations, or the first operation I use is this operation right here, right? One operation, another row operations. This is the third row operation. This is the first type, right? Interchange the two rows. And this is also the third type of row operation. So I use 3 row operation to transform this matrix